with me.
It's recording.
Okay, so it says then, a plus b squared simply means a plus b times a plus b. And what is that? Well, I'm about to use what I like to call the distributive property. And the distributive property says that I can distribute a plus b through to the other a plus b's. And so this is really like a plus b times a plus a plus b times b. Whoa. And now I apply the distributive property 2 more times. Some people might call this foiling. I call it applying the distributive property 3 times. First once, and now again. And now, if you so desire, we may combine like terms. And that seems to be what Ben was talking about. So we have a squared plus 2ab plus b squared. That is squared. Okay, smart students, please compute a plus b cubed. Why don't you?
Why are we doing this?
No, put your hand out. No, do it. Everyone has to do it.
Can we like just write out the formula?
Is there? I mean, this is kind of.
But like you have to do it throughout the work.
Or you could use the introduction.
Okay. What is a plus b cubed? Well, by definition, it is just a plus b times a plus b squared. That's not really definition, that's just a fact about how multiplication works. And as I have previously computed a plus b squared, it's kind of like a recursive type thing going on here, right? This I have learned just a second ago for the very first time in my life. That a plus b squared was equivalent to a b plus b squared, and now I merely have to multiply by another a plus b. And now I'm going to say something pretty deep. Multiplication by a plus b is simply multiplication by a added to multiplication by b. So when I multiply through this expression by a plus b, what I'm really doing is just multiplying through by a cubed plus 2a squared b plus ab squared, and then multiplying through by b. Yeah. Okay, and we get a happy formula, which some of you might just know by heart, because it's a formula which comes up often enough that it's just like good to know it. But if you don't know it by heart, well, there it is. We just computed it out. Okay, let's do another one. What is a plus b to the 4th?
No.
Go. Yes, William. Yes. No, Rafi, put your hand down.
It's just yeah. I forget if I accidentally.
Okay, yeah, we're stuck in a kind of a magnet program vortex in which there are like 8 of you who know things, but I suspect that you don't really know anything. You just kind of know some things, but your understanding, who knows, it might be total, but probably not.
Fancy formula on Armable.
Okay, good.
I didn't learn it through a fancy formula in Arnold. You can learn through it.
Grace, do a plus b to the 4th.
It's a to the 4th.
No, quiet. Do it. You need to just like, yes, you need to become, what's the beam on the binomial. Engage in the action.
I already done this. The way I found this out was by manually doing this out in like 8th grade.
He knows that. So a plus b to the 4th is a plus b times a plus b cubed. And hopefully, okay, I'm not just doing this to just like annoy you. I'm doing this because I'm trying to get your brain to follow a certain pattern over and over again. What are we really doing? When we raise a plus b, we raise a plus b to a higher power, we're just taking the previous one, multiplying by a, then multiplying by b. And by doing that, can someone tell me what is happening as I multiply through by A? What sort of like happens? Give bang. You said it a minute ago. What happens as I multiply through by A? Yeah, get this man a microphone. What he said is, as we multiply through by A, of course, the power of A goes up in every single one of our expressions. So when I do the multiply through by A step, every one of the A exponents like gets a little boost. A boost by 1. And then when I multiply through by B, every one of the B's gets a little boost. Also, it is considered default whatever by convention. We write the things in alphabetical order. And then we may, if we so choose, combine like terms. So how many of these A cubed B's do I have? 4 of them. What am I doing? And I have 3 of these, and I have 3 more over here. So I have 6 A squared B squared. How many of these A B cubes do I have? 4. And how many of these P do I have? Okay, so that is a great formula, which some of you just know because you just know it. If not, this is potentially the first time you've ever seen it before. And by the way, while we're at it, like what is A plus B to the 1? It is A plus B, that's probably worth mentioning. And also A plus B to the 0. 1. Okay, so what we are investigating today is something called the Binomial Theorem. It's a very grandiose name, and basically all it is how if you need someone, if someone is like, just tell them, you can just tell them, yo, put your head down. Cheat well. It's the only time in your life you're going to tell them. Okay. You hear it? That's me, it was just a joke. Okay. Okay. Whoa! Attachments! Alright. Okay. Good. Wait, we're back. So the binomial theorem tells you what happens when you raise a binomial to a certain power. Cool? Say cool. Cool. Okay, and what I would like now for us to do is to go around the room and make some basic kind of observations. Let's start with, where should we start? Tiara, give me one observation. It could be very, 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 like, basic.
Whoa. The power that you're using to multiply A plus B is the same power that you get on just the A term and just the B term.
Yeah, like I think you're saying that like that number is always that number?
Yeah.
And that number, yes. So Tiara would like to point out to us that we're always going to have like an A term by itself, we're always going to have a B term by itself, and the highest power is the power that we're multiplying out. Okay, we got a lot of hands up. Richard Costa, give me one.
I just drew this really cool triangle.
Okay, he's going to talk something about some triangle thing. Okay, I'm going to just,
No
I'm going to just
spoilers.
not call on him.
They're trying to
Things with single power things have the same
Yeah, that there's always just seems to be just one of these. Is that pretty much what you're saying?
where you have
Oh, she's noticing that that number is like a 4 here, right? This one? Yeah. She's like that term is like a 4, but here it's like a 3 and here it's like a 2. So I think what she's saying is when there's only one of one letter and some of the others, then the coefficient appears to be a 4. Rohit.
The coefficients are part of the triangle.
Okay, so I don't know what triangle you're talking about, but can we say everything there is to say without talking about the coefficients? Forget about the coefficients for a moment. I think there's even more basic observations to make. Yeah, Ben?
The number of terms, once all like terms are combined, is equal to the power plus 1.
Yeah, that's pretty interesting and definitely worth mentioning, right? A plus b to the 1, there are 2 terms. A plus b squared, there are 3 terms. A plus b cubed, there are 4 terms. Everyone see that? Can you give me an explanation of why, when I raise a plus b to a certain power, there are 1 more than that number of terms?
I guess it's because you have like 2, there's like 1 with a cubed, 1 with a squared, 1 with like a, and then 1 with a to the 0. So it's, I'm using a to the b cubed, for example. So
Yeah.
for each of those.
Okay, good. Let's would someone else like to speak to this fact? That there's 1 more, yeah, Noah.
There's like a term with a to the n, a term with a to the n minus 1, all the way down to a term with a to the 0.
Yeah, he's saying something about like all combinations are possible or something like that, Rafi.
The powers, the sum of the powers of a and b are equal to n, and they're every possible pair of numbers that add up to n.
Yeah, that seems really important, right? Notice how here, take a plus b cubed, for example. Here we have 3 a's, here we have 2 a's and a b, here we have an a and 2 b's, here we have 3 b's, right? So the sum of the exponents on the a and the b is the power that we're raising it to. Can I get an explanation for that fact? Why is it, and over here for a plus b to the 4th as well, how come the sums of the powers of a and b seem to always add up to 4?
Because you're like multiplying by that, so you're multiplying by like a term a or b, right? So every time you're multiplying it, you're just adding 1 to every term. So like, in the first one you have 1 term and then you multiply, right? So then a times b is 2 because a and b, you keep on multiplying.
Yeah, you see what he's doing? He's applying my deep fact from 5 minutes ago, which is the multiplication by a plus b. Just multiplication by a plus multiplication by b. So what he did there was a kind of like a little mini proof by induction almost. He said, well look, here, with I have just a plus b, I have like 1 of each or whatever, right? They both have power 1. And then, what does 1 do when 1 multiplies through by a plus b again? Well, the a is going to get a boost of 1, and the b is going to get a boost of 1. So every term is going to have now power 2, right? And then, notice here, every term has power 2, right? A squared, ab, b squared. And now, a plus b cubed is just, again, I multiply through by a, again, I multiply through by b, and I add. So as I'm multiplying through by a, every one of these terms is going to go up a power. The a is going to go up a power specifically. When I multiply through by b, the b is going to go up a power, but then the total will always be like 1 power higher than the previous one. Is this feeling like, does everyone understand what I'm talking about here? Okay, anything else to add before we start talking about the coefficients?
Oh,
Yes.
yeah, I was gonna talk about coefficients.
Yes. Yeah. We're gonna come all back to that. Okay. At this point, I think we are prepared to say things about like a plus b to the 7th, for example. What is a plus b to the 7th? Well, the only thing left that I don't understand is the coefficients. But do we all just agree that it's going to be some number of a to the 7th? How many? Probably 1. That seems to be the pattern. I might even just write that as like, yeah, I think it's going to be 1. And then what should the next, someone who's never heard of this entire topic before, what would the next term be? Ben?
It's 7.
Well, okay, yeah, the coefficient, but what's the
Coefficient
term?
would be 7, a to the 6th b.
A to the 6th b, and he thinks that's going to be 7. I'll write that in as like maybe true. And then next, for someone who doesn't know anything about this, what did we just learn? Yeah?
I don't know what the coefficient's gonna be, but I think
Yeah, good, me neither.
a to the 5th times squared.
Yeah, we just have everything in combination, right? And then next, keep going. Someone else? A to the 4th b to the cube. And then we're going to have some number, can I just keep going? Some number of a cubed b to the 4th, plus some number of a squared b to the 5th, plus some number of a cubed b, what happened? Yeah, no, oops. A b to the 6th, plus some number of b to the 7th. and I probably think this is gonna be 1, and I probably think this is gonna be 7, but I'm not totally sure. Okay, so I'm gonna call the binomial theorem basically done. The only problem is to figure out what the hell these coefficients are. And if I can figure out what these coefficients are, then I will consider this problem like solved. Is everyone with me? Okay. Alright, and now it's probably time to start talking about this weird triangle thing that everyone keeps rambling about. What's up with this whole triangle thing? Would someone like to talk about the triangle? Rafi, talk to me about this triangle thing.
It starts at 1 and then
Yeah, what's it called?
Pascal's triangle.
Yeah, there's this thing called Pascal's triangle. Some of you have heard of this, other people have not. Actually, just out of interest, raise your hand if you have never heard of Pascal's triangle. Oh, you've all heard of it. Is this like in the middle school curriculum?
Wait, it
Oh.
sounds familiar.
Sounds familiar, but it's like whatever. Okay, good. Okay, keep talking. How does it work?
You start at 1 at the top middle.
Put just like a 1 up there.
And then you go down and a bit to the left and you put it in 1 again. Okay, kind of look at. And then you go down, straight down from 1, 2 layers. Okay, you can do that. Okay, you go
Oh.
straight down and you add the 2 numbers that are above it.
Yeah, then you like add those 2 and then that becomes like a 2.
And a blank tile is just a 0.
And you just
It's
click on
only
one.
ones.
Yeah.
And
Okay.
then you keep going.
Oh, I see. You're pretty, okay. Yeah, so we've got a 1 and then this number is like 1 plus 2, which is
3.
3, and then 2 plus 1 is...
3.
Assume zeros around it.
Yeah, you can also, William says you can also imagine that this whole thing is like living in a sea of zeros everywhere. So there's just like everywhere zeros. And then you are like, you know, yeah. Okay, and then this is like 1, and then that's like 4, 6. Does everyone see how we're getting these numbers? Just adding the parents. Okay, wait, have you seen these numbers before, this particular distribution of coefficients? Holy crap, over there, it's exactly the coefficients that are appearing so far. And this would be like 1, and this would be faster.
5, 10, 5, 1. You're 2.
2 tens.
1, 6, 15, 20, 21.
Okay, and then it would be like 1, 7, 21, 35, 35, 21, 7, 1. Okay, so this is a really, really cool. This is called Pascal's triangle. You can spend months of your life just sitting around thinking about Pascal's triangle and looking for interesting, fascinating patterns, which there are everywhere. Oh, by the way, if I am going to conjecture, I'm going to conjecture that a plus b to the 7th, that the coefficients are this row of Pascal's triangle. Yeah, by the way, that's true. All right, and why that is the case is totally unclear to me at this moment. And I bet there are some of you who also have no idea why. You just know there's a triangle. Maybe Rafi does, but others of you perhaps have no idea. They know that there was a connection because someone told you between these things in Pascal's triangle, but don't actually see why. I would like to understand fully. First, can we just quickly talk about let's just look at Pascal's triangle for a minute as its own like interesting sort of thing. Can we talk about some patterns in Pascal's triangle? Oh, the people that their hand on.
Well, on like the ends, like just second, or like and like next to the 1, it's like consecutive, which makes sense because you just keep on adding 1. It's like,
Yeah, she would like to mention that this is 1, 2, 3, 4, 5, 6, 7. So that's kind of interesting. I'll say a silly one, which is just all 1s on the outside. So keep.
So like on the 7th row, right? There's no 14, 28, and all that. So like there's no multiples of 2 for that row.
Okay, I think he's observing that these are all multiples of 7. Right? Is that what you're talking about?
I think he's
Saying
saying
they're
that
all
there aren't
odd
any
multiples
even
of
numbers.
They like skip multiples of the row number.
I don't think it's about multiples because these aren't multiples of 6. I don't know. Yes?
The third row in is the triangular numbers.
Oh yeah, that's a kind of a cool thing. Yeah, there are these so-called triangular numbers. The triangular numbers are the numbers which are like the sums of the first n numbers. Did we talk about this before? I feel like we did, right? The first triangular number T1 is 1 because it's the sum of the first 2 numbers. The second triangular number is 3 because it's the sum of the first 2 numbers. The third triangular number is 6 because it's the sum of the first 3 numbers. The fourth triangular number is 10 because it's the sum of the first 4 numbers. And he is noticing that these are in fact the triangular numbers, 1, 3, 6, 10, 15, etc. That's pretty amazing. Even more, yes?
So like for the row for like the slanted line of ones, there's no change. For the next one, it's changed by 1. For the next one, it's changed by 2.
Damn.
4, 5, and
Yeah, look, watch this. No change, she says. Change by 1. Up 1, up 1, up 1, up 1, up 1. Change by 2, up 3, up 4, up 5. Now it's like up 3, up 6, up 10. Now the gaps between these are like the triangular numbers. Okay, that's interesting. All right, Rafi, anything left?
If you called the top row is 0, the sum of all the numbers in a row is 2 to the row.
Yeah, that's kind of fascinating. Add up 1 plus 4 plus 6 plus 4 plus 1. What do you get?
16.
16. Add up 1 plus 3 plus 3 plus 1. What do you get? 8. Add up 1 plus 5 plus 10 plus 10 plus 5 plus 1. 32. Yikes! Coincidence? Probably not. So many things to talk about. There's even like way more like advanced, interesting and fascinating, amazing patterns like built into Pascal's triangle. One of the people who invented calculus like started by just screwing around with Pascal's triangle for like a year, and then he invented calculus. Okay. Good. All right. So if this were a crappy pre-calc class, like MCPS or whatever, yeah, you heard me, people watching at home, then I would probably just do that little thing over there where we multiplied out numbers, then I would make the triangle, and then I would just be like, oh, look, the coefficients of Pascal's triangle seem to be the binomial coefficients, and then I would just say, binomial theorem, ooh, everyone gets an A, and we would move on, and we would just do a bunch of problems. No! I have no idea why this is true. I do not understand this at all. I'm more confused than ever. I still don't understand why these two have anything to do with each other. Okay, so what we will now do is we will take a step back. What? No. What? I don't know. There's been no question, so there's no reason to raise your hand. Yeah, what?
Can I talk about the path thing?
No.
Because that's related
No.
to that. Though.
No. Good. Thank you for asking. No. Okay. What I'm now going to do is I'm going to make a giant tree. My claim is that one of the things which is obscuring our understanding of the binomial theorem is the fact that we combine like terms. So what we should now do is not combine like terms. If you want to pick that up and move it over there like next to Grace, it might be better. Or you can not do that. All right, so take a piece of paper out, go to a fresh piece of paper and go landscape. And what we're going to do is we're going to build all binomials in the manner that we did over there. Alright, so, and it's going to be a tree, so the top of the tree is like 1, naturally. And then we're going to indicate multiplication by A by following left on the tree, and multiplication by B going right on the tree. In other words, if I have the number 1, which is A plus B to the 0, and I want A plus B to the 1, well, I just multiply by A plus B. And multiplication by A plus B is like multiplication by A, then multiplication by B, and add. So if I multiply 1 by A, I get A. And if I multiply 1 by B, I get B. Behold, that is A plus B to the 1. Okay. William, thank you for your positive encouragement. Now I will do A plus B squared. Well, A plus B squared is just that times A plus B. And what is multiplying by A plus B really, if not merely multiplying by A and multiplying by B and adding the result? But this time we are going to not combine like terms because I claim that combining like terms is what obscures the understanding. So if I take A and multiply by A, I get A squared. If I take A and multiply by B, I get AB. Here I get AB. And here I get B squared. Everyone with me? Okay. Now, that is A plus B squared. Now I want A plus B cubed. Well, what do? Multiply by A plus B again. And what does it mean to multiply by A plus B? Multiply by A. Multiply by B. Add. So multiplying each term by A is equivalent to like going left on the tree from the previous term, because I've now established the convention that following the left branch is equivalent to multiplying by A. Everyone with me? So I'm going to stop writing that. So here I get A cubed, here I get A squared B, here I get A squared B, and here I get AB squared. And I'm going to also multiply through by B, giving me A squared B AB squared, AB squared, and B cubed. Behold, that is A plus B cubed. Is everyone following the logical structure of this? Would anyone like to make a comment already? One of our mysteries from 30 seconds ago just got a proof.
So this maps out every single path you can take by multiplying.
Wait, before you get onto that, there's just pick one little tiny thing about Pascal's triangle that we noted that we didn't have an explanation for that we now do. William.
It's a binary tree. So if you add
It is a binary tree. Yeah, the total number of terms that you have at any particular row prior to combining like terms is going to be a power of 2, right? There are 8 terms prior to combining like terms. And if you look over there at that a cubed plus 3a squared b plus 3ab squared plus b cubed, if you think of those ones with coefficient 3 as being really like 3 separate terms, there are 8 of those, right? Okay, so that's pretty cool. Okay, do one more row. Everyone do it right now.
What are you doing? Why? Patrick, you can talk. Yeah, you can talk. Like, why are you
Doesn't happen right now, so just get the whole thing.
There's nothing happening right now. So, oh, you're trying to zoom out, you mean?
Yes.
You just
What do you think I was doing?
fixing the camera.
Just fixing the camera. Mr. Rose moved.
Okay, I think that looks good. Everyone with me? Okay. Let's now do some thinking. Question. How many a cubed b terms are there? Notice that when you don't combine like terms, the question of what is the coefficient becomes simply the question of how many terms are there. Suddenly, I find myself in a counting problem. Let's just locate all of the a cubed b terms. Where are they?
To the left.
Here's one, here's one, and here's one. Any more? No. Answer? 4. Okay, well that's consistent with what I got over there when I just mindlessly multiply everything out, and I noticed that the coefficient of a cubed b was 4. Does everyone see how I've rephrased what is the coefficient as a counting problem, right? Okay, what does every one of these a cubed b's have in common?
They're kind of like more on the left side.
He says kind of like more on the left side, but he didn't raise his hand. Neo, what do all these a cubed b terms have in common? How did I get there?
Well, you multiply like more by a than you would by b.
Yes, specifically?
Specifically like 3 times by a and then like 1 time by b.
Yeah, let's go through them one at a time, right? How did we get here?
You multiply by a, and you multiply by a, and you multiply by a, and you multiply by b.
Yeah, Neo's like, dude, this particular a cubed b term resulted from starting with 1 and multiplying by a, then b. Oh man. Neo, where did this second a cubed b term come from?
You multiply by a, you multiply by a, you multiply by b, and you multiply by a.
Yeah, I got here by going a, b, a. I got here by going a, b, a. I got here by going b, a. In other words, every one of these terms results from a distinct path through the tree. And how many paths through the tree are there, which end in a, which terminate in a cubed b terms? Answer: the number of paths which involve going left 3 times and right once. And we've just solved that problem like 15 minutes ago, right? How many ways are there to go through the path, to go through a path of length 4 in which I go left 3 times and right 1?
4 factorial over 3 factorial.
Yeah, it's like just 4 choose 3 or 4 choose 1. So this is 4, and I'm going to call this 4 choose 1. What is the 1, or what is the 4? The 4 is the path of length 4 through the tree, and the 1 is the number of times in which I had to go right. Right? Because every time I go right, that's like one of those times. Okay? Doing the same question again. How many a squared b squared terms are there? Well, I can just count them. A squared b squared, a squared b squared, a squared b squared, boom, 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 and that's it. How many? 6. So if I want to know the number of a squared b squared terms, then this is equivalent, the answer turns out to be 6, and it's equivalent to, well, how did I get here? I went left, left, right, right. Here I went left, right, left, right. Here I went left, right, right, left. Here I went right, left, left, right. Here I went right, left, and I went right, right, left, left. In other words, every path through the tree in which I went right precisely 2 of those 4 times resulted in a different one of these a squared b terms. And so what is this? This is just 4 choose 2. Of the 4 paths through the tree, let 2 of them be rights. And we can just kind of keep on doing this. How many a b cubed terms do I have? Different color. 1, 2, 3, 4. And what is that? Yeah, that's 4. So how many a b cubed terms do I have? Well, now it's how many paths through the tree in which I went right 3 times.
Simple, right?
So it's 4 choose 3.
If you want to go to like the second thing
Who gets
to the
it?
left, on the fourth
Raise your hand if you kind of like had heard about all the thing before, but you had no actual understanding of where the things go. Does this make all make sense? Schaefer, you happy?
Go over to the
You're good. Were you going to say all this, or were you going to say something slightly different?
before choose
some of that.
Pretty sure
Okay.
that's what it does.
How about a to the 4th? How many of those are there? 1. How many a to the 4th b to the 0 terms should I expect? How can I think of that 1?
4 choose 4.
Yeah, but keeping with the pattern, it's actually
Yeah.